Now this question illustrates a useful concept, that is, time period can be found using either Newton's law of motion, or time period can be also found using writing the energy conservation equation. So there are two methods to find the time period. Let me first make the diagram and then we'll discuss what is the problem all about. So there is a ceiling, and through this ceiling there is a disc that is attached, and this disc contains a spring constant K. This spring is fixed at one end. Now this side we have one mass that is attached, and the mass is a small m. Now let me read the question. So this says a mass m is attached to a spring constant K via a frictionless pulley. So this pulley is frictionless, of radius r and mass m. So radius is r and mass of this pulley is capital M, as shown in the figure. Determine the frequency of vertical oscillation of mass using first Newton's law of motion. So we have to use Newton's law to find out the time period. Okay, basically this question says there is a friction. This is not frictionless. There is a friction between this thread and the pulley. So there is a friction. So that this is basically pure rolling case. So if this thread moves by this disc moves by angle theta, the thread moves by distance r into theta. So there is a friction. But this is a case of pure rolling. This friction will not do any work. This friction, no slipping. So this is a case of pure rolling. So with the disc, this thread rolls pure rolling situation. So this is a pure rolling. Now what we have to find? We have to find time period first using energy consideration. So let us say equilibrium condition. If I write, initially this spring will be a stretch because this mass will pull this spring this side. So let us say this spring is just stretched by distance x naught. Are you getting? So if this string is stretched by x naught, now I can write there is a force that is acting in this direction mg, and this force that is acting t. So if I write equilibrium condition, now this thread is basically not, this disc has mass. So tens on this side and tens on this side will be equal initially because system is astatic. If this is moving, in that case tens on this side and tens on this side will not be equal. But this is a static situation, so tens on this side and tens on this side will be equal, and this is the same as this tension. And this tension on this side there is a force that is kx naught. So tension will be written as kx naught. And if I write equation for this, tension is equals to mg. So I have equilibrium condition, that is kx naught is equals to mg. So this is my equilibrium condition. Now what will happen if I displace this disc by angle theta? So in that case, if I displace this disc by angle theta, so let us say this angle is a small angle and the displaced angle is theta. So this mass that is initially it was here, now it will fall by some distance, and after falling, so this will come here. So this is the final, so this is the initial situation of block and this is the final situation of block. So this will fall up to some distance, and this distance will be, the fall will be, this distance is theta, so this rotation is r into theta. So this will fall by r into theta distance. Similarly, this spring will be further elongated. Initially it was elongated by distance x naught, Now this has moved by r theta, so this spring has also moved in this direction by r into theta. Are you getting? Now what are the forces that is acting if I write equation of motion? Now the tension both sides it will not same. Are you getting? So let us say tension this side is T1, this side tension is T1, and this mass is in motion, so I cannot say this tension is simply T1. Of course this tension, let us say T2, and this spring will elongate this side, so this will try to extend this spring this side, a string this side, so T2 will be basically equals to K times x naught plus r theta. Are you getting? So this spring will try to pull this thread this side, and the spring has elongated by x naught plus r theta, so spring will apply a tension K x naught plus r theta, and this side we will have a tension T1 this side. So let us write equation of motion. So this mass, let us say this mass is going in the downward direction with acceleration a. So if I write for this mass, what are the forces that is acting? mg is acting in the downward direction, T1 is acting in the upward direction, this mass is going with acceleration a in the vertical direction, and let us say this is rotating with angular acceleration alpha. Now this is a case of pure rolling, so a is equals to alpha into r. So I can write a is equals to alpha into r, because this is a case of pure rolling. So this will be rotating, and this is also having a linear acceleration. So linear acceleration of this point should be same as that is linear acceleration of this point is a. This should be alpha times r. Now let us write equation. So mg minus T1, this is one equation, is equals to mass into acceleration. Second equation I will get for this. So T1 into r, this will try to rotate in this way, but T2 into r, that is opposite way, minus T2 into r. So this is torque is equals to I alpha, and let us say this is a disc mr square by 2 or solid cylinder. So I into alpha, and alpha is nothing but a by r, so I can put a by r. Of course this r is a small r, so this is a small r. In the next line I will change this one. T1 minus T2 is equals to mr square by 2 into a by r square. So a by r square, so r square goes, so we will have T1 minus T2 is equals to ma by 2. So this is my equation number 2. And T2 is nothing but x naught plus r theta. So let us plug this value. T1 minus T2 is k x naught plus r theta. This is equals to mass into acceleration ma by 2. Are you getting? And further I can write the same equation. So let us plug the value of T1. T1 is mg minus ma. So you see from here I can write T1 is mg minus ma. So this is equals to mg minus ma minus kx naught minus kr theta. This is equals to ma by 2. Now if you see the equilibrium condition, mg is equals to kx naught, so this cancels out. Now this a goes that side, so we will have minus kr theta is equals to m by 2 plus m into a. And a is nothing but r alpha, so I can write kr theta is equals to m by 2 plus m. And I can write a is equals to r alpha, that is alpha is d2 theta by dt square. So r goes, so we will have m by 2, so let us say m plus 2m by 2 into d2 theta by dt square. This is equals to minus k times theta. So we will have d2 theta by dt square. This is equals to minus 2k divided by m plus 2m into theta. So from here I can calculate omega. So omega is what? Under root 2k by m plus 2m. So this is a simple harmonic motion with omega is 2k by m plus 2m. Now what is my target is, I want to achieve the same equation using the energy method. So this we have done. This equation I have achieved using the Newton's law of method. So now the same equation, the same omega I want to get using energy concentration. So let us call this method as the energy method. So what we will do is, so let us say at any point of time, this disk is rolling, let us say with angular velocity omega, and this mass is going in the downward direction with velocity v, and there will be a spring. So let us say this spring is just stretched by distance x at any point of time. Are you getting? So this string is attached. You understand? So what are the energy we have at this point of time? If I write all energy, so let us say first I write kinetic energy, potential energy of a spring. Potential energy of a spring. So this will be nothing but half kx square. So this is the x that this point of time there is the stretched string. There is nothing like x naught in this case. I am calling x naught plus x as a x. That is the total stretch, total elongation of a spring. So potential energy is half kx square. What is the kinetic energy of this mass? Kinetic energy of this is a small m. So kinetic energy of mass small m, and I said this moves with velocity v, so this is half m v square. Now I have to write kinetic energy of disk or kinetic energy of cylinder if you have solid cylinder. Now this is rotating, so I can write half I, that is mr square by 2, half I omega square. So this is the kinetic energy of disk. Do we have to write any another energy? Let us think. Do we have any other energy? Can we have potential energy of mass m? Potential energy of, this is the mass capital M, I think. The lower one is the bigger mass, capital M. No, this is just small m. So I have to write capital M, this is small m. This is capital M. So do we have potential energy of this mass? Now let us try to understand, if I make my datum here itself, so this is my instantaneous datum. So if I say this is my datum, after the displacement wherever this mass is, this is my datum. At this point of time, I can set my datum at any point. So if it's my datum, in that case potential energy of this mass is 0. This is my line. At this point of time, this mass is here, and this is my datum. So potential energy is 0. Are you getting? So let us try to write all energy, and then try to differentiate this equation. So total energy will be, so total energy of this system will be half kx square plus half mv square plus half I omega square. And this energy has to be constant because this system there is no dissipative force. So energy cannot be lost. So this energy is constant. So if this energy is constant, I can multiply by 2. So I will have kx square plus mv square. And I can write v is equals to r omega. That is a case of pure rolling. So v is equals to r omega. So let us replace r square omega square as a v square. So this becomes plus m by 2 v square, that is equals to constant. Are you getting? Now if I take this x square this side and v square common, so kx square minus kx square is equals to m plus m by 2 v square. Now if I differentiate this equation, so minus x square is 2x, dx by dt is v is equals to, this is m plus m by 2, v square is 2v, and the differentiation of b is dv by dt. So you see dx by dt is nothing but v, so v goes out. 2 also goes, so I will have minus kx is equals to m plus m by 2. This is equals to dv by dt. So I can write this is dv by dt can be also written as d2x by dt square minus k divided by m plus m by 2 into x. So again you have the same thing. So omega will be in this case k by 2m plus m, and this 2 goes on the top, and if I take root, so this is my omega. So this is the time period for this motion. If I consider the energy consideration, we get the same time period. Omega we are getting the same. Either you do. Now only important point we have in energy consideration method is taking the potential energy of mass, that is a small mass, is 0. I have set my datum in such a way that after displacing wherever my mass is, my mass is basically moving with velocity v, disk is rotating with angular velocity omega, a spring is elongated by distance x, stretched by distance x, and at this time wherever my small mass m is, I say at this is my datum. At this point my potential energy is 0. Are you getting or not? So from here we can differentiate the equation. You will get the omega. If you want to set your datum at initial position, in that case you have to write energy in a spring is half k x plus x naught plus x square. In that case you have to apply the equilibrium condition again. So if you want to set up your, so let us say somebody wants, so this is my equilibrium condition, and when the equilibrium condition is there, this is expressed by distance x naught, and let us say somebody wants to set the datum is here, so he wants to set the datum. So after the datum, so if you displace the mass, in that case, so now if you displace, so in this case a spring is basically stretched by x naught plus x, and now this mass will go down by x naught plus x. Are you getting or not? So if you displace by x, this is the equilibrium condition, so this mass will go down by x because x naught is included here. So now in that case, if you want to write total energy, what you will write is, you have to write total energy is half k x naught plus x whole square, and this is again half mv square, half I omega square, mr square by 2 half I omega square, and this is v, so half mv square. And you have to also write potential energy of this, so this is coming down, so I have to write minus mgx, that is the potential energy we'll have in this case, minus mgx, and this has to be constant. If you want, even you can differentiate this equation and you will get the same result. So let me do it for you. So let us cancel 2 throughout. So we will have, let us differentiate first. So we will have this 2, so this goes, so we will have k x naught plus x. I think you are able to understand. So this is x naught plus x, and differentiation of 2, so 2 will be here. So I am differentiating this, and differentiation of x is dx by dt. So let me write dx by dt also. Are you getting or not? So I am differentiating this term. So first I am writing, so this 2 goes out throughout. So I have to multiply by 2 here itself. So let me multiply, or I can cancel 2 here itself. So let us cancel 2 and dx by dt. I have cancelled this 2 plus half omega square. So this is r square omega square, that is v square. So this is written as half m by 2, and this is b square. Differentiation of b square is 2b db by dt. And now this is again half m 2b db by dt. Are you getting? And here we will have minus mg x, and differentiation of x is dx by dt, and that is side is constant is 0. Now if you go to the next term, so what we will have, now let us try to club these two terms together and in the beginning. So we will have this 2 goes, this 2 goes, so we will have m plus capital M by 2 b dv by dt. I think all of you are getting this one. There is nothing, no mathematics. B divided by dt, and now we will have plus kx naught plus x. So let us say kx naught and plus x also. Let us put dx by dt is v minus mz dx by dt is v is 0. Let us cancel v throughout. So I will have m plus m by 2 dv by dt, and this is plus kx naught. Basically I wanted to cancel that in the last line, but I am not cancelled. So this is kx naught plus kx, v I have already cancelled, minus mg. This is equals to 0. So now kx naught is equals to mg, that is the equilibrium condition. If you see your back, equilibrium condition we have written, that is kx naught is equals to mg. So now from here we are getting the same equation, m plus m by 2 into dv by dt is equals to minus kx. Are you getting? So from here you can write dv by dt, this is equals to minus k by m plus m by 2 into x, and dv by dt can be written as d2x by dt square. This is equals to minus 2k by 2m plus capital M into x. So from here you can find omega. So omega will be under root 2k by 2m plus m. So even it does not matter what method you prefer. You can take initial as a datum. You can take yourself datum at the same point when this mass is basically displaced by distance x. But in that case, the total spring stressed, I have considered that as a x. Whatever method you prefer, both will be good. This method is a better option. So you see, you write the equilibrium condition and then you displace by x. That is a good method, because this method is applicable in both cases. It's applicable in energy consideration as well as in force consideration. So you can apply any one of the method. So we'll finish it here. We'll go for the next problem.